Hello, everybody. I'm going to go through the solution of question 28 in algebra sections in the course Maths1151 at University of New South Wales. Excuse me. And this is an interesting question, but as we remind ourselves, this is a H question, hard question. It is unlikely that you are going to be examined by. Very, very unlikely to be examined by. But it's very nice. It's a thinking question. Let's solve it. We have a matrix cosine theta minus sine theta, cosine theta. And we would like to prove that this matrix is an orthogonal matrix. And then we would like to show that for any vector in R2, x to the origin, qx to the origin are exactly the same value. And thirdly, we would like to show that the Q act as a rotation on R2. First, remind ourselves what is an orthogonal matrix. Orthogonal matrix means that the transpose is equal to the inverse of that matrix. This is equivalent to say that transpose times Q and the transpose itself and its transpose will give you us an identity matrix. This identity matrix here is in the 2 by 2 dimensional matrix. As we know, this is just 1, 0, 0, 1. This is what we need to prove for this matrix. So we will take the transpose of this matrix. This row will be a column. So cosine minus sine theta. And this row will be the column. So this is the transpose of Q, and that is Q. Let's multiply them together. So cosine square plus sine square. So this is this entry. This row dot product with this column, we will have cosine times sine theta, sine plus sine theta times the cosine theta. So that is 0, which is this position. And this row with this column, we have minus cosine theta, minus sine theta, cosine theta, plus cosine theta, sine theta will be 0 with this position. Here with this column, we have minus sine square theta, plus minus will be plus sine square theta plus cosine square theta. We know that sine square theta is equal to 1 and cosine square theta is equal to 1. So that will be just an identity. So we prove that Q transpose Q is identity. And also we need to prove the other one, or we can use the transpose of the transpose by just taking every places with the transpose will do the job for us as well. What I'm saying is that you can say in another way, or you can do it just as a multiplication, or you can say Q transpose Q, this is what we proved, is the identity. And we can take the transpose in everywhere. So we will have Q transpose, Q transpose. Oh, that will not work. That will be just that will not work. So you need to multiply these two matrices. I was just thinking whether it can be done. Okay, so the Q matrix here is orthogonal. That's what we show. Now the second part, we have any vector, and let's apply the Qx because we would like to figure out the distance between x and 0 is equal to the distance between Qx to the 0. That's the origin. X is any vector. Let's take any vector. And what is the Qx, how it looks like? Let's have a look. So this is Q times x. So this times this and this times this will give us this entry. This is cosine theta x1 minus sine theta x2. And this row with this column will give me this entry, sine theta x1 plus cosine theta x2 will be this entry. Now, assume that D denotes the distance, Euclidean distance in R2. We know how to calculate that. So this is the x vector, and the 0 is the origin 0, 0 vector. D is the denoted distance between these 2 points, these 2 vectors. So that will be the square root of x1, x2. So since this is 0, 0, x1 minus 0 square plus x2 minus 0 square, and then we are taking the square root, will give us the distance between x and 0 for any vector in R2 with the origin. Now this is the qx vector. So this is the first component, and this is the second component. So this is the x-axis component, this is the y-axis component. And now, similarly, we can calculate the distance, right? This is what I'm doing here. I'm calculating the distance dqx and the 0 origin. So there must be, this is a vector, 0 vector. There is a similar thing. This is the first component minus the 0. And we are taking a square plus second component minus 0 square. And then we are taking this square root. So exactly the same formula that we are doing, but this time the vector that we have has a huge x component, there's a huge y component. That's all the differences. Now we need to organize this a little bit and see what we can find. Opening up this square, we have sine theta, sine square theta x1 square plus a sine square theta x2 square. And then this times this twice. This is 2 x1, x2 sine theta cosine theta. And from here, we will have the plus of those. We also have the squares of this and square of this. So we have the cosine x1 here square here, x1 square here, cosine square here, cosine sine square here. That will give us 1. This together, this one will give us 1 x2 square, and this one cancel out. And then we have, this is 1, this is 1, we have x1 square plus x2 square, and we know that this is exactly the distance in dx0. So dx0 is equal to dqx0. So the distance between x vector to the origin is equal to the distance between qx vector to the origin. So that was the second part of this question. Let's have a look. The last part of this question, we would like to prove that Q acts as rotation. So we need to look at the looking at the how Q acts the whole space. In order to be able to understand the whole space, we need to look at the any vector. And we know that any vector can be written as a linear combinations of the standard basis elements. So in order to be, it is enough to look at how the action of the Q acts on the standard basis elements, because standard basis elements will give you the whole space. All linear combinations of the standard basis elements will give you the whole space. So it is enough to look at the basis elements and how it is being affected by the Q matrix. So this is what I'm doing here, right? E1 and E2 are the standard basis element, and every vector is a linear combinations of these basis vectors, so it is enough to look at the Q action as a rotation on E1 and E2. That will simplify our world a lot, and the basis concept is very important for the vector spaces, because vector spaces are usually the ones that you're at least dealing with are infinite. And in order to be able to tackle that problems, how to handle an infinite objects in the finite versions of yourself, here is basically to going through the basis element allows you to observe an infinite objects with a finite way. So that was the idea. Let's have a look how Q acts on E1. That's the matrix, and this is the E1. This vector, this row, sorry, multiply with this. I have only cosine theta The other one is 0. So this is the first entry. This times this, I have only sine theta. That's sine theta. And if I look at the E2, multiplying by E2, this one will give me only sine theta. This times this will give me only the cosine theta. So 1, 0 goes to the cosine theta, sine theta, and 0, 1 goes to the minus sine theta, cosine theta. Now, theta is a rotation by theta in the anticlockwise direction. I just, this is obvious from here, but let's have a look what we are doing here. So this is the vector E1. And we are moving to the rotation theta up to here. So this point here will be cosine theta, right? The x component of this point, this vector here, this point here, will be cosine theta, and the y component of this one here will be sine theta. This is exactly what it is. So this vector goes to this vector, right? E1 becomes this vector. It is rotated by the action of Q. This is 1. And if similar things happens to the E2, then we can say that Q acts as a rotation. Let's have a look. This is E2, and this is theta. And here, this point gives us and the cosine theta for y value, and minus sine theta for x values. So this is exactly this vector. This vector is this point, or this vector. And E2 moves to this vector. Basically, E2 has the rotation, anticlockwise rotation to this vector. As you see, this one and this one is the new one. This is the E1, E2, and this one is the E2. Let me get that one. So this is the E2. This is where it moved. Again, you have a basis. So QE1 and QE2 is another basis for R2. And every vector can be written as a linear combination of these ones. Not every matrix does this, but this is a very special matrix. And it does it. It rotates. All perpendicular structure also is preserved as well. So everything is rotated by theta. And QE1 and QE2 is a new basis. It's a perpendicular, it's an orthogonal basis, and it is just a rotation of the structure E1 and E2. I think it's enough for this question. I think it was a very nice question to solve. I hope you will enjoy the beauty in the solution as well. Thank you very much.